the next talk, which will be presented by Professor Ioannis Kevrekidis. He's currently the Bloomberg Distinguished Professor at the Department of Chemical and Biological Engineering, Biomolecular Engineering at Johns Hopkins University. His research interest is multi-scale computations and modeling of complex systems. He has developed in the past something called equation-free approach to complex systems. And now he is working on linking with modern data mining and machine learning techniques to develop something what he called an equation-free and variable-free approaches to modeling the complex systems. Today's talk is on the machine learning tipping points. So, yes.
Thank you for the invitation. For the organizers, it is the second time that I missed being here. I really regret this. I was looking forward to it. Given that we've kind of taken 12 out of the 30 minutes, I was thinking of talking about 3 things. I'll probably try and talk about 2 things and see how much I can do. I had okay, this was supposed to be for fun. It's an economics-based, agent-based model. You have 50,000 agents that live between -1 and 1. And -1 and 1 have to do with whether you want to buy or sell. And 0 is neither buying nor selling. And there is all kinds of things about how they interact and how do you go jumping, going back to 0, selling and going back to 0, or buying and going back to 0. I will skip all over this and just tell you that you have 50,000 interacting stochastic differential equations. And what I'm going to show you is what they do. So I run them. And what you see here is a version of the behavior. These are the 50,000 agents. This is the PDF of the agents. This is the mean, and this is the fluxes at +1 and -1. Here you see that the agents look like a partial differential equation that goes to a stationary state. This parameter 42, I didn't tell you the details, has something to do with how much attention they pay to each other. If they pay 42 attentions to each other, everybody goes to a steady state. You go to 46.5 attention to each other, and then what happens is that they go okay for some time and then they explode. Everybody rushes to go to 1. So this is a place where you have a transition between normal behavior and a different, very different explosive basin of attraction. And you mentioned equation-free stuff. So 20 years ago, we developed techniques in which you run brief bursts of the agent-based problem, and then you do macroscopic calculations at the coarse-grained level. So you run the agents for a little bit, and then you take an integration or a Newton step for the coarse-grained reaction coordinate of the agents. Here, the reaction coordinate is not the scalar, it's the entire PDF of the agent distribution. You can use this to accelerate stuff. So what you see here is something that was called coarse projective integration. This is the CDF for the agents. You run them a little bit and then make a macroscopic run of the coarse-grained observables. You reinitialize the fine-scale simulation briefly, and you see there is jumps. So the idea is that you save macro time by doing these brief bursts of simulation. That's not the important thing. The important thing is, and again, I am going very quickly through this, the important thing is if you don't have a macroscopic equation, you can still solve it without writing them down by doing brief bursts of microscopic calculation with the right initial conditions and then processing them nicely. It's not, again, so important what the algorithm is. Let me show you the result. What you see here is the parameter value. Think of it maybe as a temperature. It's not very fair. This has to do with how much attention they pay to each other, or maybe like the strength of an interaction potential. And what you see is a stable branch of solutions and then an unstable saddle type branch of solutions. And what we did, we were able to do the coarse-grained bifurcation analysis of this without deriving the macro equation, finding the bifurcation diagram. At the bottom, what you see is coarse-grained stationary distributions of agent, but stable ones. At the top, coarse-grained unstable saddle type distributions of agents. So it's a bit impressive to find saddle type distributions of agents that are stationary, because simulation will not go there. What's the idea? The idea is that if you find them and then you sit at the right transition state, at the right unstable stationary distribution, if you kick it a little bit downwards, it will go to the stable stationary distribution. And if you kick it a little bit upwards, then it will explode. So the idea is that one uses coarse-grained bifurcation calculations to find the transition states. And now, having found these transition states, you can do all kinds of things, like, for example, write coarse-grained controllers and keep the unstable solution stabilized, which is what you kind of see here. So you use macro knobs to stabilize unstable stationary distributions. But what I really wanted to talk to you about is that if you go very, very close to this coarse turning point, a tipping point, then if you sit very close to it and you run the simulations, the PD is really, the partial differential equation for the density is really not a very good model. What happens is you see that you do have fluctuations, and at some point the fluctuations will kind of drive you to the other side and escape. So what's the idea? You go very, very close to the tipping point, which was discovered by the first coarse-grained round of simulations. And then what you do is that you find some good mathematics-based reaction coordinates close to a tipping point that's a turning point. What is a good coordinate? It's the unstable eigendirection of the saddle. So what you'd see here very quickly is to find the first coarse-grained round of bifurcation diagrams, find where the tipping point is, and then use math to suggest what would be a good coarse-grained coordinate, in particular, the unstable eigendirection of the saddle, and then go and identify an effective potential in this variable. You do this, and then you can kind of go ahead and find distribution of escape times and so on and so forth. The thing that is interesting is not so much that you can do that. This was done with Kramers-Moyal estimation, and then with diffusion maps and geometric harmonics for estimating the surrogate model. What was interesting here is that in addition to doing it, as I kind of told you, in a mathematics-inspired way, the reaction coordinate, you can also do data mining. Our particular poison is diffusion maps. And with the diffusion maps, you find that the escape is more or less effectively one-dimensional. And therefore, what you can do is that you can use the diffusion map coordinate now to learn the effective surrogate model. And the important thing of all of this first part of the chat is look at this diagram. It's a very messy diagram. It's supposed to be a straight line that you see here. Here is the effective coarse-grained coordinate. It says intuition. It's the one that is based on the bifurcation diagram and the unstable eigenvector. Here is the coordinate that comes from just data mining the results. And the important thing to see is that they're practically one-to-one with each other. So the interesting thing, if you want, is the comparison here of coarse-grained coordinates that come from math versus coarse-grained coordinates that come from data mining, and testing that they're one-to-one with each other. This is another tipping point example. This is a paper we did a few years ago before COVID, which kind of becomes interesting or important again. This is running a very large 100,000 network of people. They are infected, susceptible, recovered, but then the connections are adapted. If you know that your friend is sick, then you don't go and visit them. So you run this, you still have to find coarse-grained coordinates for it. Now the tipping point, if you look at it, it's over here. This is one of the parameters in infection rate, is a subcritical Hopf. So you do a coarse-grained bifurcation diagram on the first round, you find the subcritical Hopf, and now you see it's not just the same kind of usual escape from a saddle in one dimension. Now you need to escape from a crater in 2 dimensions. And what we do is that we first, to find coarse coordinates, we need distances between graphs. So we use graph metrics to find distances between graphs, do diffusion maps, find coarse-grained coordinates. And maybe I will sit a little bit on this slide. Here, what you see is the coarse-grained coordinates colored by the physically meaningful coarse-grained coordinates, like the density of susceptibles and infecteds. What you're supposed to see with your eye is that the color is suggests that the physically meaningful and the data-driven ones are one-to-one with each other. So one of the interesting things is to think a little bit about interpretability of the coarse-grained coordinates. The second interesting thing is that instead of doing Kramers-Moyal and then using geometric harmonics to find the surrogate model, so a kernel maze method to find the surrogate model, what we've done now is that we have used neural networks that are templated on numerical stochastic integrators, Euler, Maruyama, Milstein, and Point, to identify the effective SDE, so that when you have the effective SDE, you can kind of go and do the rare event calculations with the surrogate model based on the effective SDE. And this is something that is the third thing that I wanted to talk about. I'm looking at my time, maybe I can make it. Well, what I wanted to discuss as a second subject, let me skip over this. A long time ago, since it is a conference where there's a lot of molecular discussion, I should throw something molecular also. We came up with Bill Gear, maybe 20 years ago, with something called computing in the past with forward integration, which is run your simulation a little forward, estimate an effective time derivative at the coarse level, and then take the problem backward. Run forward a little bit, estimate at the coarse level, and go backward. So this is effectively going backward in time, going up an effective free energy gradient, not in the directions that things explode, but in the slowest, most probable direction. You can think of it, it's a paraphrase, but it's not completely fair, but it is a way of kind of doing a sort of mildest ascent on the fly. Not exactly, but it's a comparable idea. And so what we did a few years ago with Gerhard and Roberto Covino and a number of people, Elio Chiavaccio was the first author in the paper, is to do an exploration geometry that is based on the-fly data mining and biasing based on coarse grain geometry. Think of it as a revealed exploration geometry. What do? You run a little bit, and you see that over here. You do data mining and find that your behavior is effectively low dimensional. And now that you have the low dimensional geometry, you go to the boundaries of the low dimensional geometry, do a little bit of differential geometry, bias the initial conditions, create initial conditions with Klum for the numerical method, and then run unbiased simulations again. So unbiased simulations, find the exploration boundary, perturb it geometrically, reinitialize and run unbiased, do it again and again. You can think of the effective free energy surface that you don't know is like a dark carpet in a very high dimensional space. You run a little bit, you do data mining of that, you go to the boundary of what you did, you need to find the boundary, there's good tools for doing that, do a little differential geometry, create good biased initial conditions, do it again and again and again. And we call this intrinsic map dynamics because we use the on-the-fly revealed, if you want, geometry to go effectively up a free energy surface. You need to be able to simulate unbiased. You do that. You need to do data mining. You can do that. You need to find the boundary. Here we used alpha shapes. And then it's kind of important when you create the new initial conditions in core space, you can go back. You need to go back to the full space. There's a lot of work on doing that these days. And for example, does it using GANs. So we used to do it with umbrella sampling in the coarse variables, which were principal components at the time, local principal components, so Plume. This is doing it in alanine dipeptide, which is trivial. After 2 rounds, you fold the little thing. This is something that we did with Gerhard, that was done by Roberto Covino. It is much more protein-like. There's an MGA dimer, and there was a long simulation, a long Martini simulation of the MGA dimer. It had found a few transitions. What we did, and this is the summary of the PNAS, is this picture. This slightly shitty colored part is the part that you find from a long, I think something like 6 months, Roberto said, unbiased simulation. Here you see, if you want 1 day of simulation, the times are not correct, but they give you a feeling. 1 round of simulation, data mining, find the boundary, extend, and then this is the 2nd round, and then this is the 3rd round, and even from the 2nd and eventually in the 3rd round, the dissociation of the dimer was found that had never been found before in the direct 6-month simulation by the Martini. So what is the point again? The point is exploration biasing, but not doing it with just blind active learning, if you reinforcement learning, if you want, but doing it based on the geometry of the surface that you have so far discovered. This is kind of the fun thing that I wanted to show. Maybe this is the last time that I will show it. I wanted to share the sound, and I think I am sharing it. So I don't know how many of you remember seeing the Indiana Jones movie.
Only in the leap from the lion's head will he prove his worth. It's impossible. Nobody can jump this.
Indy! And you must hurry! Come quickly!
remember the movie is really fun but happy. But because of what he does, now. Out, what we do is that we actually see the path. So what I wanted to tell you in this is that metadynamics actually fills in the ravine with sand, while the kind of thing that we do, if you want, throws out just enough sand to cover the effective low-dimensional free energy surface. So the idea is that, again, you can use the geometry of what you've discovered up to now in order to make more parsimonious paths than filling the ravine with sand. The third thing that I wanted to tell you is something I was listening to what Professor Gordon was saying in the morning. It has to do with gauge invariance in data mining. How do we do our data mining? So as long as we observe different views of the same thing, the latent space that we're going to discover is going to be the same. This is something that we've been working on for the last maybe 4 or 5 years, and actually in a way for the last 10 years, but consciously the last 5. You kind of know that if you use kernel methods to do data mining, the important thing is the distance. Yes?
Nara, wie geht's? Bist du dran?
I heard somebody, but I don't know what they said. Was it for me?
No, you can go ahead.
No, okay. So think of the horizontal axis as being a divine space, like a Platonic space, the most beautiful way of representing something. And then we need distances between conformations. And then based on these distances, we can go on and do Gaussian process regression or kernel PCA or diffusion maps or whatever. Let's say that on the left axis is Ioannis, and Ioannis does not see the same thing that Plato sees or God sees, but sees something that is a distorted version of the truth. This means that the distances of the same observations in my space are different than the distances in the God space. However, if I don't only compute distances, but I also, do you see these little kind of circles around here? If I do a little jiggling of my simulations very close to the initial problem, so if I perturb the problem a little bit and look at how this perturbation ensemble looks like in my space, I can use the perturbation ensemble shape to estimate the slope of my own observation curve. And if I have the slope of my own observation curve, then I can scale the distance so that it looks very much to the 4th epsilon power, like the distance in God space. And if this is, I don't know, if this is Pratyush, and Pratyush has his own view and his own measurement device, and then he looks at the same 2 events, but now the distance in Pratyush space is really, really different. If Pratyush also observes the little jiggle around the initial and the final point and uses it to scale his own space distance, then both I and Pratyush can map to Platonic space and fuse our data to each other. So the idea is that it is possible to take very different observations of the same thing. If you want, I really am not a chemist, so forgive me if I say stupid things. You can take chemical information, spectroscopy information, molecular dynamics information. You observe it the right way, then it is possible to fuse all of these very systematically by doing the right data mining. If you look at the shape of this, it looks very much like a lens. I did it on purpose. I can take my observations and map them to Pratyush like light going through a lens. What is the necessary magic? The necessary magic comes from Singer and Koifman, and it has to do with perturbing your initial conditions and your final conditions systematically a little bit. And I told you that we've been working on it for 10 years, but not consciously. We had a paper with Singer and Koifman back then for finding good reaction coordinates this way, but we didn't really realize that this was gauge invariant data mining. And as I said, the magic is that you use not the usual distance metric, but you use a Mahalanobis metric, which is based on the local covariance of the noise, not globally for the distribution, but in the neighborhood of your particular measurement. This looks like neural networks. It is neural networks, but it is not neural networks in the sense of doing something. This is a numerical neural network way of solving the same eigen problem. You take the data and you try and put them in a latent space, but in this latent space, the main characteristic is that the covariance of the noise at the initial point becomes a perfect circle. So you're trying to z-score the data. You try to find a perfect space in which the noise is perfectly diagonal and amplitude 1. This is a way of taking very different measurements and registering them in a systematic way. Whether you do it with eigen problems or whether you do it through a neural network solution algorithm, it does not matter. The name here is a local conformal autoencoder. It is an autoencoder, but it imposes local conformality. The main idea is you have this is, let's say, the Platonic space. This is one invertible measurement of the Platonic space. This is another invertible measurement of the Platonic space. The idea is that by doing this kind of data mining, you can turn them into things that are modular and orthogonal transformation. They're very, very easy to match. So this is a systematic way, if you can get the little perturbed measurements around the main measurements that you have, that you can fuse information and also hopefully also register, calibrate, and fuse models. Why is this important, I think, in our days? I think in our time this is important because everybody, given data, will make their own neural network or ML or gray box or whatever model of a problem. The different models by different research groups will more or less agree on the data. So the question is, are they the same models or not? And what I told you is a way to register between different models and establish whether they are diffeomorphic from each other, whether my calculation and your calculation can be calibrated to each other. So we had a paper on matching between different neural network models. It's been around for 2 years. You will forgive the old professor, the computer scientists say, what a wonderful idea, but the application, it should be on something that has to do with MNIST. It will not pass again in the conference. This is just sour grapes on my part. So I want to finish with something that maybe you will find entertaining. In Renaissance, people found how to do the right perspective. They found a way to paint exactly the way that the work looks to you. They found a way to make a model that looks exactly like nature. This was very painful, and you see that they took a lot of trouble to be able to make models that look very much like what happens in nature. But then photography came along, and then, it was not just enough. You had to show the mood when you see something, and you had to have impressionism. What I really want to tell you is that if this is nature, this is the Vitruvian Man by Leonardo, then you would like a model to be like a perfect mirror. You would like it to show you exactly what you see. And the idea is that generally a model is a slight deformation of truth. It's a little bit off. I want to take this idea. So this is like a Luna Park mirror. You see a little distortion of yourself. What I want to do is to take this idea and reverse it. What if what we see is really a realization of something else, more perfect? So this is one molecule, this is another molecule, and this is the third molecule. They all kind of have qualitatively the same behavior. Why don't we find a mirror that allows us to map my molecule, your molecule, and the third molecule to a sort of prototypical normal form? I know that it sounds a little bit funny, but again, the idea is, how about sculpting our latent space so that it is beautiful? Beautiful might be linear, like Koopman. Beautiful might be integrable. Beautiful might be unitary. And so the idea is to not just ask for a useful latent space, but ask for a latent space in which the dynamics are Hamiltonian, unitary, integrable. Let me just say that one of the nice things about this is that if you have very, very different measurements of the same thing, then it is also possible to fuse them. So this is kind of where I wanted to end and say that well, as you see, I am much more of an algorithm person and not so much of a person that knows about the chemistry of the transformations, but I find very exciting the idea of trying to do the data mining from different sources in a way that the results are very easy to match, are matchable. Okay, that was it. I even managed to finish on time with but 5 minutes for questions missing. Sorry, I started late.
Thank you, Ioannis, for really great talk. We have one question in the chat box. Lucy Delamote asked that, can you recover the equilibrium distribution from IMAP-D?
Yeah, thank you. Thank you for the question. So this is something that I always personally have. Okay, let me put it this way. If you can parameterize, if you have a nice parameterization of your low dimensional manifold, then you take a grid on it, you calculate the potential of mean force locally, and you reconstruct the thing perfectly. So yes, you can, because you have found the geometry, and now with the parameterization of the geometry, you can do local calculations and get local drifts and diffusivities in your effective Langevin. There is no reason for this search to give you an equilibrium distribution at the end. If this search finds the geometry, then you can get the equilibrium distribution by just post-processing. I'm not saying it's easy. I'm just saying, if you have good reaction coordinates, then you revisit them, put a grid, calculate local drifts and diffusivities, and get the effective potential. So you can get it, but it is not a result of the search itself. The search itself is not obliged to give you at the end an equilibrium distribution. Did I answer?
Yeah, I think she said thanks. So
thank you.
Answered correctly. Any other question from any other participants? Okay.
Okay.
If there is none, then let's thank Ioannis for this wonderful talk.